Impagliazzo will speak on recursively applying constructive dense model theorems and weak regularity.
Okay, thanks. So this work is motivated by the general type of question that Peter was talking about last week in the mathematical conversations. Namely, you have a general phenomenon that many mathematical objects are best understood as a structural component, a structured component that has some characterization, plus a random component that's characterized by not being characterizable, as looking like look like it was sampled from some distribution. Of course, it's a fixed mathematical object, so what does it mean to say it looks like it was sampled from some distribution? And Peter pointed out that identifying the right distribution is often the interesting part. So what I want to talk about is at least one sense in which we can formally define what such a decomposition consists of and prove that in some sense, at least in principle, these decompositions exist, okay? No matter what mathematical object we're talking about. At least as far as the type of mathematical object that I'm going to be concerned with. It probably doesn't apply to you know, it applies, this is sort of a unification of approaches to many things, but not to everything. So I'm trying to, I'll be sweeping, but not that sweeping. Okay? So, the kind of object is, we'll have some universe, and because I prefer discrete things, I think of the universe as finite but large. And within that universe, you have a smaller subset, S, and S is the object that we want to characterize. Well, if I just sort of left it at that and say, well, that's not very interesting, pretty much any finite subset of any other finite subset is characterized just by its size, and what else can you say about it? So we have to say what kind of quantities or ways we're going to measure elements of this subset, that, what are we interested in about this universe and about the subset. So we'll have a class of tests, and I'm going to think of tests as Boolean functions on the universe. And those are the properties that we're interested in. Okay? And pretty much everything I'm going to say would generalize to bounded functions, that are real valued. They don't really have to be Boolean, but I prefer Boolean just to be concrete. And okay, so that's what we're interested in, the type of property that we're interested in about S. And so, for example, in complexity theory, the set might be a set of strings of length L that are possibly outputs of a pseudorandom generator, and we were interested in tests that are easily computable. So are describable, so Boolean functions computable by relatively small circuits. Okay? Or in another application that we'll look at is in graph theory, where we want to look at a fixed graph and say in what sense is, can we come up with a model for where this graph, what kind of random graph does this graph look like? In that case, the universe is all possible edges of the graph, so all pairs of vertices. The set is the actual edges of the graph, and then the tests are usually cuts in the graph where you look at two disjoint sets of vertices and say, does this edge go from one set to the other? Okay. And there are many other examples, but those are the two I'm going to focus on. Okay. Okay. So So we first want to say, well, we want to talk about dividing up, as far as this kind of tests are concerned, dividing up into the set into a part that looks structured and a part that looks random. Well, what if it were all looking random? Shouldn't we have a notion of what it means to sort of look random? And the first thing is, we want a notion of what it would mean to look completely random, and then let's refine that to a notion of what it would mean to look like it's distributed according to some fixed distribution. Okay? So, so first, we'll say that the set looks random, like the uniform distribution on U, if for any test in our collection of tests, if we look at the probability that this test is true of a random element in our set and compare that to the overall probability for a random element in the universe, these should be small. So if we pick a random element and apply the test, we shouldn't be able to tell whether the random element's coming from S or coming from all of U. Okay? So that's what it would look like to mean that S is completely random. But if it's not completely random, it might look like a random model. Okay? So let's say what kind of distribution we could be talking about. So a fairly general or completely general way of viewing distributions on U that's going to be convenient is we're going to give each element of U a numerical value in the, would definitely be picked sort of what's the probability that we would include this element in our distribution. Okay? So you can think of the distribution as first picking, flipping a coin for every element with bias mu, and then picking a random subset of things that came out 1. Okay? And so we can define, how large, if this were just Boolean 0, 1, then it would reduce the uniform distribution on the ones, and we could look at the size would be the number of ones. More generally, we'll say the size of mu is the expected number of ones, so it's just the sum of mu of x for every x in the universe. Okay, so this measures how much randomness would be in this from a random sample in this measure. Okay, and induces the distribution. D sub mu is just using the size to normalize. Okay, and then we'll say that the actual set that we're concerned with looks like this random model mu if the same thing holds that holds for the uniform distribution up here, that for every test that we care about can't distinguish between a random sample from S and a random sample from that distribution. So this is clear?
Your expectations, are you over the universe, are you assuming that everything has equal weight then, or is that?
So here I'm assuming everything has equal weight. Okay. And note that this is one reason why I'm keeping everything finite is I don't have to worry about measures or anything. So everything I could also, okay. Again, for simplicity, I'm thinking of S as a set of inputs, but we could do everything with S being a measure on itself, being a measure on U, and thus inducing a distribution rather than being a fixed set.
And your set of tests, you have conditions on the set of tests that you want to be able to...
Well, so the only conditions we have is that the set of tests have to contain the I think I wrote it somewhere. It has to contain the constants and has to be closed under complement. Okay. Yes?
So can I go back? What do you mean by function computable by small circuit on a very large set?
Okay. So, we would have some quantitative measure of how large the circuit would be. So tau would be indexed by the size of the Boolean circuit. we could think of the universe as L-bit strings, and then a Boolean circuit can do one Boolean operation on two of its two previously computed either inputs or previously computed values in one gate. And so we'd be counting the number of gates that can be done.
But the values are zeros or ones for each element of S. That's the input, right?
Right. So every element of S would be represented as an L-bit string. Okay. So an element of S would be S1 up through SL, and then these would be Boolean valued, and the circuit could perform operations on S1 through SL and also on previously computed values.
Is there a relation between that and polynomials of low complexity?
There are several relationships, but they're kind of complicated. I mean, so the thing is, you could identify each Boolean operation as a polynomial, but then many equivalent circuits would be computing distinct polynomials. So just because two circuits compute the same values wouldn't mean that they have the polynomials. And so very generally, it's hard to reason back and forth.
But you could make your notion of
I could be looking at algebraic circuits rather than Boolean circuits, for example. And everything I'm about to say is perfectly general. I guess the one thing is you'd have to make the algebraic circuits output Boolean somehow. Okay. So this issue of how I should say that this, in the complexity context, this notion of looking random came up in work on pseudo-random generators in the early 80s in work of Blum, Macaulay, and Yao. And then this general notion of when two sets look the same came up again in cryptographic applications in work of Goldreich, Macaulay, and Rakoff. And then the question that arose in the 90s was we wanted to actually say, so this was talking about when things looked perfectly random, and that was a good measure of when a pseudo-random generator was doing its job. But as an intermediate step in the design of pseudo-random generators, we wanted to say, if we've got some kind of flawed construction of a pseudo-random generator, how much progress have we made so far? And so we came up, Hassad, myself, Levin, and Luby came up with this notion of pseudo-randomness, pseudo-entropy, I should say, where we're looking at the maximum amount of randomness that a distribution looks like it has. So I want to say there's the actual amount of randomness of a distribution, and then there's the amount of randomness it looks like it has. And so what you can do is compare look at all the distributions that look like your set, and of those, pick the one that has maximum entropy, and that's, in some sense, the pseudo-entropy of your distribution. Okay, so that characterizes, and more recent work of Barak, Shaltiel, and Wigderson characterized when the pseudo-entropy was very large. Okay, actually that so in a different context, the same kind of notion of when a distribution doesn't necessarily look random, but looks like it has a lot of randomness to it, came up in the work of Green and Tao, and later Tao and Ziegler, in the form of a dense model theorems. And the question was almost the same. So you had some set S, you had some set of tests tau, and you wanted to know when there was a model mu that was large, so had a lot of entropy. So size of mu is at least, say, delta times the size of the whole universe. So it looks like it's a constant fraction of the universe. And S is epsilon indistinguishable from the distribution induced by mu. Okay. So they came up with a partial characterization of when such sets have, when such models exist. Okay. And it turns out that their characterization was equivalent to that of Barak, Shaltiel, and Wigderson for when the pseudo-entropy of a distribution is high. And it's not so, when you look at it abstractly, these two notions of the pseudo-entropy being large and having a dense model are exactly equivalent, are exactly the same. So it isn't too unreasonable that they would come up with related characterizations. Although the one in BSW, the conditions are weaker than those for that Tao and Ziegler came up with.
And what do you mean by large?
So delta parameterized as how large, because we want the distribution to be size at least delta times the whole universe. And epsilon is parameterizing how close, and tau is saying what kind of tests we're interested in. Okay. So okay. So before I state some versions of the dense model theorem, need say so it would be nice to say that you know, somehow whenever we're doing something this general, there's always some kind of trade-off. So what's the trade-off? In that we're going to look at the you know, sort of look at the densest models, but that with respect to tau, but we're actually going to be comparing them to what we could do in slightly more complexity, with a slightly richer class of tests, rather than directly comparing them to what else we can do with just tests and tau. So so I'm going to use the notation b sub k of tau as all functions computable from knowing t1 through tk where the ti's are in tau. So sort of the closure under Boolean operations involving k inputs of tau. And for this talk so often we're going to get a stronger characterization. The Boolean functions we're going to be considering are really just ky's and, ky's or, and ky's majority. But for this talk, it's not going to really matter. Okay. So, okay. So, what we want to know when S looks big. And so what we want to say is S looks like it's big if it doesn't look like it's small. Okay, that either, when would S look like it's small? Well, if we had a test tau that contained all T and tau, that contained all elements of S, but not much of U, that would certainly be a witness that S is small. But we don't have to have this strict containment. It's enough if this test T contains a lot of S, but not a lot of the universe. Okay. So the more general picture is a witness that S is small is a test T where the relative size of the intersection of S and T is much bigger than the fraction. So the fraction of S that has T is much bigger than the fraction of the whole universe that has T. So T is say a delta epsilon witness of sparsity. So maybe like I should say it another way. So is an epsilon witness of delta sparsity if if the expectation of T of S, I'm going to actually change the order. Okay. Sorry. Okay. So if the expectation under a random thing from the universe is smaller by a delta fraction from the expectation when we just pick elements of S and minus the epsilon. Okay. So so this alone could only hold if S is at most a delta fraction of the universe, even without the epsilon. But so why do I have this epsilon in there? It's just saying, well, if the tests were almost never true in either the universe or S, it would be some sense a witness that S is small. It would still be a reason why S is actually small, but it wouldn't be it would be something like a statistically unobservable reason. Because even if you were given many samples from U and many samples from S, both of these, you would estimate both of these probabilities at 0 with high probability. And so you wouldn't actually know that this one's much smaller than this. Okay. So is this clear? So that this can only happen if S is small. And putting the epsilon here means that we basically only need polynomial in 1 over epsilon samples to be able to tell that this means, reliably tell that this means S is small. Okay. So then the dense model, or one version of the dense model theorem, says that if I should say so if no such test exists, we call S epsilon delta pseudo-dense.
This is all within your test script T.
Sorry?
This is with respect to your test script T.
Yes. I think I got it right. So because we want this we want the universe to be much smaller than the.
Oh, okay.
So I could put the epsilon plus epsilon over on this side, but.
And you get, I mean, this is one side and you use the complement sort of, you also think about it.
No, we're actually, because we're interested in how big S is.
Oh, I see.
We're not interested in how,
Oh,
you know, S, usually S is a teeny set,
Okay.
and we want to say it looks large.
Oh, okay, okay.
Okay. So, so like it's a sparse graph, but it looks like it came from a dense graph. You know, it's randomly sampled according to a probability distribution. Okay. So, then the dense model theorem says for k equal polynomial in 1 over epsilon and 1 over delta, if S is epsilon delta pseudo-dense for tau sub k, then S has an epsilon model mu with the size of mu being at least a delta fraction of the universe for tau.
Instead of tau sub k, do you mean d sub k of tau?
Yes, I do. Sorry, that was my old notation. Okay. So it says, if there is, so basically saying, if there isn't a reason why tests in tau reveal that S is small, then there's a measure that's big that looks the same as S. You know, as far as tests in tau go, it tells the same story as S. So, you know, S is pretty much thought of as chosen, sampled. The elements of S can be thought of as sampled from this distribution. Okay. So we're gonna actually like show how to derive a weak regularity lemma, but not the strong regularity lemma.
So are you going to give us some examples of how this works?
Yeah. Okay. So actually, so what it's actually going to give us is not even the weak regularity lemma per se, but it's going to show us, so even these regularity lemmas assume that the graph is, or are only interesting when the graph is dense. Okay? But what we're going to get is a version. What you get is a version, and this when the graph is sparse, and you want to say it looks like a dense graph and has such a dense model, just like in the regularity lemma. So I'm going to come back to that, but it looks like I'm not going to do anything new if I don't keep on going. So, and so I'm actually going to hopefully get a slightly improved version of a weak regularity lemma, if I can get through things. Okay. So okay. So this okay, so this was, you know, I said this was in the BSW paper. It was in the context of computational complexity. It was a slightly weaker version was done with stronger assumptions, was used by was proved by Tao and Ziegler in to clarify the previous Green and Tao proof that the primes had arbitrarily long arithmetic progressions. But then I should say was looked at by Trevisan, Tulsiani, and Vadan, trying to connect the two approaches from complexity and combinatorics, gave a new proof, and their new proof had some quantitative improvements over that of Green and Tao and Ziegler, which were also independently discovered by Gowers, but also their new proof. They pointed out that there was some similarity between this work, the proof of the dense model theorem, and a previous result of mine improved by Thomas Hohenstein, the hardcore set lemma. And I'm not going to say what the hardcore set lemma is or what it has to do with the dense model theorem. I did that in a previous talk a couple of years ago. But I will say just one thing, that there's an algorithmic proof of the hardcore set lemma. Okay? And if you follow that algorithm, the equivalence, and apply it to the show that use the algorithmic proof of the hardcore set lemma to give an algorithmic proof of the dense model theorem, then you get one strengthening of the dense model theorem that I find very interesting, where you not only show that this model exists, but in some sense construct such a model. So the
hardcore set lemma? What did you say? It was hardcore
set lemma. Yeah. So I said I wasn't going to say what it was, but since you asked, okay. So it has this kind of flavor of decomposing a set is something into a known part and an unknown part.
Maybe that's all I need to know.
And yeah, okay. So I'm gonna, and so if you look at that proof, then the only change is that the model itself is definable using the same number of tests using the same number of tests that we're using. That's the trade-off between sort of the gap between the proof of smallness and the witness of largeness.
Is it of importance in this theory that you can make a model explicitly, or is it what you get out of the explicit construction?
Well, so I'm going to actually just start saying why this is interesting and why just using this dense model theorem with the constructive form as a black box, we can get this kind of decomposition of a set into its structured part and its unstructured part.
Computer science, is it of any importance to actually have this construction?
Oh, for example, we'll be able to use this to get constructive versions of the weak regularity lemma and generalizations. So from the complex, actually in the original sort of computer science approach, we were using this to look at pseudo-randomness. I don't have any direct applications there, but it actually does have algorithmic consequences. And you can, for example, use it to derive algorithms that find regular representations of graphs. And okay. So So okay. So this says that if we've got something that's pseudo-dense, then there's a model for it and more one that we can construct. What if we have an arbitrary set, though? Okay. Well, what we can do is keep applying this. What this says is actually that either we construct a model for a set, or we find some kind of piece that looks more structured than the rest. Okay. So actually, maybe before I start that part, I'll want to explain, especially for Peter's series of questions, give one motivation for why it's interesting that this model is constructive. Okay, so let's go to the case of graph regularity. Okay, and
Can you review what it says?
okay. Right. So okay. So what we get is say that if S is epsilon delta pseudo-dense for b sub k of tau, then that means if there isn't some kind of witness that S is small, something that is a giveaway set that S is small, that's describable by k tests within tau, where think of k as a small, almost constant number. Okay, then S is going to have a model where it looks that's also definable by the same number of tests that that is dense and looks like S. Okay, and actually, what I claim is that in the case of graphs, this property is much more interesting than this property. So we're really interested in the existence of a describable model, and that's rather than the fact that the model looks large. Okay. So the first thing to note that is that any t prime in that's a describable. Here T is the set of all tests that say, does your edge go from set A to set B in the graph? And if you have any Boolean combination of such tests, you can just sort of you have it also depend on whether the edge goes from A prime to B prime. Okay. Well, you can just sort of divide up your universe, keep on partitioning the universe up to those that belong to A, those that belong to both A and A prime, those that belong to just A prime, and so on. And so you get an exponential number of just plain cuts that cover this test T prime. Okay, so So even though pseudo-density is with respect to this closure tau, in the case of cuts, it really amounts to the same thing, except with an epsilon exponential loss, exponential quantitative loss. Okay, so so in the case of graphs, what this is going to say is that either there's a cut where the density in your graph of edges from A to B is much, much larger than what it should be, okay, by this 1 in delta factor. Okay, and these two things are not too small, are constant size, or we get a model that's describable by this fixed number of cuts that tells that describes your graph, as far as cuts are concerned. So what that model looks like, okay, since it's describable by only a small number of pieces, again, we can partition the whole set of edges up into, that means an exponential number of pieces. And in the model, between each of these pieces, since all the tests are going to come out the same way, there's a fixed density, a fixed probability, Pij, that you think of as the probability that an edge between those pieces exists. Okay? And then what this says is that if you look at any actual cut in the graph, the fraction of edges that actually crosses this cut is almost within a small error determined by these edge probabilities. You look at the number within each component and look at the probability that you get under this random graph model, and that tells you within a small error what fraction of edges in your graph actually go through that cut. So that's kind of hand wavy. But this was this weak regularity for sparse graphs was known, but it was an actual result, and this shows that. One special case, of course, is if the graph really is dense, then you get always, the first condition doesn't happen, and so you always get the second condition. Okay. So, okay. So what I want to, okay, so, well, okay. So how can we get this general decomposition? And I think I'm not going to actually go through calculations, but just draw some pictures because I'm running low on time. But say that we've got our set S, and we just keep on applying that dense model theorem until something happens. Okay? So the first time we apply it, what do we get? We get some test T. We either get a model and then we're done. We've got S looks like it came from this probability model, and that's a dense model, and we're done. Or we get this test T1, where the fraction of S, T1 is relatively small within the whole universe, but it uncovers a disproportionate chunk of S S. Okay. So, okay, so well, that's making some progress to our characterization of what being in S means. Okay. But we're not done yet. So let's just take away T1 and look at that subuniverse where we've deleted T1 and apply the dense model theorem again. So again, either we'll get a dense model now of the uncovered part of S, or we'll find a set test T2 that covers a disproportionate amount of
And so those intersections are what you're calling the kind of the structured part, right?
Yeah, well, so we're saying the union
It's going to
is going
be
to be at least it's going to contain the structured part. We still have to, okay, and then we're going to say, let's keep on going and even focus in on that and see if we can come up with a stronger characterization. Okay, so what we end up with is we end up with a test T in a slightly larger polynomial, defined in a slightly larger polynomial number of components. Okay, and what this has, and we will eventually come up with a model of the uncovered part of S. Okay, and you use alpha 0 to mean the fraction of S that remains uncovered when we eventually find this model. Okay, so the properties it's going to have is that if we look at the distribution D alpha T mu that says with probability alpha 0 sample using mu on u minus t. And with probability 1 minus alpha 0, sample from S intersect t. Okay, so I claim that that distribution, S is going to be indistinguishable by test in our original set from this distribution. So this is going to at least saying that mu is a good model of the covered part of S. And we don't yet have any characterization of the uncovered part. And the other property is that T of S is, T of U is less than or equal to delta so the total measure of T in particular is less than a delta fraction of the total universe, and yet it contains a disproportionate by a delta factor part of S. Okay. Okay. So now the second stage to a characterization is to say, okay, now this mu is a good characterization of the part of S that's not covered by T. And T is, S has, the part of S within T is much larger proportionately than S is within U. So now we're going to recursively let U prime be the set of ones under T, and S prime be S intersect T, and apply the same kind of characterize S prime within U prime. Okay. So,
So you're thinking of T is now all of these pieces that you pulled away?
yeah.
Okay.
Sorry, so T is the union of all of these pieces, which is why it involves a,
Prime. Yeah, okay.
and then the number of TI steps we're going to go through is roughly delta over epsilon. So it's polynomial in 1 over epsilon. Okay. So okay. So then so what's the conclusion is that if we repeat this, we'll get I don't know how to draw. We're getting telegraphing circles, and I want to say like how many of them we have to draw before they become invisible. Okay, and so we get T1, T2 sitting inside T1, T3 sitting inside T2, and so on. And the property is that if we look at the distribution, so we'll have some numbers, alpha 1 up to alpha I, that say what's the overall probability of something in S being inside T1 or not being inside T1, not being in T1 minus T2, and so on. So we'll pick I according to alpha 1 through alpha I. Okay. If we pick I, then we'll sample from mu I on Ti minus 1 if j is less than or equal to I, just less than or equal to I, and sample from S intersect Ti otherwise. Now, this distribution is indistinguishable of epsilon I from the uniform distribution on S, and Ti of U is going to be at most delta I of Ti of S, where I'm using this as shorthand for the expectation that I've been fighting against. So, okay, and each of these TIs is each of the mui's is definable by a constant number of tests in our family, and so are each of the TIs. Okay, so so we can keep on going until, if we make things depend, we can keep on going until this actually can't happen. until you've reached the log of the density of S within the universe. And at that point, what we've got is just a series of measures, mu1, mu2, up through mu i, that approximately describe being a member, are very close to, are sort of, and what this is going to be is sort of the maximal entropy model of S within some small factor. Okay. If we apply this to this general decomposition in the case of weak graph regularity, so we can, for example, pick the delta that we're using in each step of the decomposition to be a half, okay? And if G has pseudo-density, either, so pseudo-density, but actual density it implies pseudo-density. Say capital delta, we pick I to be log of capital delta. And we get a model of the edges of the graph described by k equals polynomial in 1 over epsilon and log 1 over delta cuts. So if we do the expansion, then saying each cut depends, each cut, the space of all k cuts defines 4 to the k different subsets that we could be interested in, and each subset has a constant probability. Each pair of subsets has a constant probability. Then we get a cut model of G with something like 2 to the polynomial in this 1 over epsilon log 1 over delta components. Okay. If you compare that to the weak regularity lemma of Fries and Canaan, it's this, and it's the same thing except with a polynomial in 1 over epsilon and 1 over delta, replacing the log 1 over delta. So in some sense, we get an exponential improvement in the number of components. Okay. On the other hand, I haven't been able to find any application where the delta is the sticking point rather than the epsilon. So where we do actually, our polynomial in 1 over epsilon is somewhat worse than the original one. Okay. So conclusion is that yes, we can come up with, by using this kind of homing in on any kind of set, we can come up with sort of the maximum probabilistic model that, that sort of explains the structure of the set. If it has some structured part, that's going to leap out at us at some point when the TI is all the remaining part of S, or most of it.